Another example, let's do it. 16.4. Hydrogen peroxide decomposes spontaneously into water and oxygen gas via a first order reaction. How nice. They told us already it's a first order reaction. And once again, even though there's this 2 right there, we can't necessarily always say that 2 is going to mean this is a second order reaction. That worked in our generic examples. And the reason that worked in our generic examples is because we were just saying those things go on to form products. And we didn't know what's going to happen with those products at the end. But because we've been specifically told this is proceeding via a first order reaction, we recognize very likely that 2 in there is just to balance the equation, right? And if I didn't have that 2 in there, I would have the equation balanced as H2O2 goes on to make H2O plus 1/2 O2, and that's perfectly okay. Because we recognize these aren't like 1/2 of a molecule, it's just 1/2 of a mole of molecules, right? So once again, we do have to be very careful when looking at reaction stoichiometry and reaction orders. Okay. So in the absence of a catalyst, this reaction proceeds very slowly, which is true for this specific reaction. So if a small amount of salt containing the iron 3 catalyst is added to a 0.437 molar solution of hydrogen peroxide and water, the reaction proceeds much faster with a half-life of 17.3 minutes. What is the concentration of the solution after 10 minutes under these conditions? Okay, so there's a lot less information in this problem, and at first it seems a lot more difficult, but it's not so bad once we kind of recognize all of the things that we have and what we need. So whenever we see time, like especially when something says, what is the concentration after a certain amount of time has passed, we want to think integrated rate law. That's the equation we need when we're trying to figure out how much of a reactant or even product will be left after a certain amount of time. So our integrated first order rate equation is natural log, and we'll fill that in for this hydrogen peroxide case. Natural log of H2O2 at time t equals negative kT plus the natural log of the initial hydrogen peroxide concentration. And so if we look at everything that we have here, we can see 10 minutes, that's going to be our value for T, which means we need that concentration of hydrogen peroxide at that time. That's what that T means. We have the initial concentration, 0.437 molar, but what we're missing is K. We need the rate constant. However, we were given a half-life. And we know that we have a half-life equation for first order reactions. It goes T1/2 equals 0.693 divided by K. And so that's the first thing that we're going to need to determine. Okay, so that's just going to be oh, wait a second. Aha! I was talking and totally did that backwards. So we were given the half-life. What we want is the rate constant. So we need to do some algebraic manipulation here and say now that K equals 0.693 divided by T1/2. Okay. So now that's all going to be 0.693 over 17.3 minutes. And so we can do that calculation. So 0.693 divided by 17.3, and that gives me 0.0401, and the units of that will be 1 over minutes. Okay, so I went 401 because 3 sig figs in the calculation. So now we can start plugging stuff in. We have the natural log of H2O2 at time t, and that time is 10 minutes. Perfectly fine to leave that t right there. And so now that's going to be negative 0.0401 1 over minutes times 10.0 minutes. So you can see the minute and the minute unit will cancel, which is good. And now that's plus the natural log of the initial hydrogen peroxide concentration, which is the 0.437 molar. And so now let's go ahead and calculate all of this stuff. So 10 times negative 0.0401 is just negative 0.401. And then now we've got to take the natural log of 0.437. And don't confuse that with log log, right? We've been doing that log log for pH calculations, but that's log base 10. We want the natural log, ln, which is log base E. So I'll push that button, and now I get negative 0.827. And if I finish adding those two numbers together, I'll say plus 0.401 negative, and I should get like 1.2 something. There we go. So that's now negative 1. Because we added, it's 3 decimals, 1.229, and that's unitless. And now we recognize here, finally, we've got natural log of H2O2 at time t equals negative 1.229. And this is very similar to what we did in pKa and pH calculations. When we wanted to cancel the log, the log, we raised it to the power 10. But now we have natural log, so we need to raise it to the power e. So if I take e of both sides here, that e is going to cancel the natural log, and now that just becomes H2O2 at time t. And then now I can just raise this to the power e, which on the scientific calculator, since I left this in here, I can now just say that button right there, and that gets me the right answer. Okay, so that's 0.293 molar. And if we want to just kind of look at our answer and see if this makes sense, then, well, we know that if its half-life is 17.3 minutes, then at 17.3 minutes, we should have half of this 0.437 molar, right? But at less than 10 minutes, or excuse me, at less than 17.3 minutes, we should have more than half of it left. Think about that for a minute, right? The half-life is 17 minutes, but we only let it react for 10 minutes. So we should have more than half. And we do. So we can see we've got 0.293 left. If we have 0.437 divided by 2, that's 0.2185, right? So we can see that we've got more than half left, which makes good sense.